Chapter 3 Change of State. Chapter 3.1 Latent Heat. Which one is colder? Both beakers are at 0 degrees Celsius, one with melting ice, while the other does not. How will their temperature change with time in the next few minutes? Do the experiment yourself after the video. 1. Latent heat and change of state. Both beakers will absorb heat from the surroundings, including your hands. Temperature of water in container B will rise immediately. For container A, there is some ice. The temperature will remain at 0 degrees Celsius until all the ice has melted. So container A will remain cold for a longer time. Ice is the solid form of water. When ice melts at 0 degrees Celsius to become water at 0 degrees Celsius, there's no change in molecular kinetic energy, while its molecular potential energy increases due to the change of state from solid to liquid. The energy absorbed by ice becomes molecular potential energy of liquid water, and it is called latent heat of fusion. The word latent means hidden because temperature does not rise during the change of state. The latent heat absorbed when water changes to steam is called latent heat of vaporization, which is much larger as vapor molecules are very far apart from each other. Nevertheless, they have the same average molecular kinetic energy if the liquid and the vapor have the same temperature. A. Heating curve. Let's examine the temperature change when a solid melts. Here we use Bk1Chp3, which is a wax-like substance.
Melt some solid octadecan-1-ol in a boiling tube using a beaker of hot water. Suspend a temperature sensor in the middle of the melted octadecan-1-ol. Wait until the liquid solidifies completely. Immerse the boiling tube into a water bath at 75 degrees Celsius. Run the data logging program. Stop data recording when the octadecan-1-ol rises to about 65 degrees Celsius. The temperature time graph obtained is the heating curve of octadecan-1-ol. Does the temperature of the octadecan-1-ol rise all the time throughout the experiment?
The heating curve shows that the temperature remains unchanged for a period of time in which the octadecan-1-ol was melting. The temperature at that time is called melting point of the solid. The temperature rises again when all octadecan-1-ol was melted. So what if a liquid freezes to become a solid? B. Cooling curve. The experiment continues by allowing the test tube of octadecan-1-ol to cool down.
Melt some octadecanol in a boiling tube by heating it in a beaker of hot water. Remove the boiling tube from the beaker of water. Suspend a thermometer in the middle of the liquid. Allow the octadecanol to cool in air. Read the temperature of the octadecanol every minute. Melt some ottoda K1O in a boiling tube by heating it in a beaker of water. Remove the boiling tube from the beaker of water and clamp it on a stand. Set up the temperature sensor. Allow the ottoda K1O to cool in air. Start data logging.
Again, the temperature remains unchanged for a period of time. When the liquid ottoda K1O solidifies, it freezes. The temperature at that time is called freezing point of the liquid. The temperature of the test tube starts falling again when all liquid has become solid. Similarly, the same applies to boiling point of the liquid when liquid vaporizes, and also to condensation point of the vapor when vapor condenses. Therefore, latent heat is absorbed or released when there is a change of state of matter. Example 1. Heating curve of water. Water is probably the substance that we are most familiar with. In this example, some water at 25 degrees Celsius is heated in a closed container. Its temperature increases for a short time and then remains unchanged for a period of time as shown. Obviously, the temperature T in the diagram is 100 degrees Celsius, the boiling point of water. Water absorbs latent heat of vaporization to vaporize, and you can see that the temperature of steam keeps rising when all water becomes vapor in a closed container. Visit the following website about the working principle of a rice cooker and then try checkpoint 1 on the next page.